from the University of Michigan.
So, thank you. So when I ran into Ronit in the hotel when we arrived, she was telling me how she was a graduate student here, and she was here during the earthquake sometime when the Bay Bridge sort of collapsed on itself. And she was telling me what a traumatic experience this was for her. I didn't want to tell her I was going to talk about monitoring the structural health of bridges. I thought she would be worried for a couple of days. So I'm going to tell you about monitoring bridges for their structural integrity and their health. So this started out as a project with some folks in the College of Engineering at the University of Michigan. And this seems like sort of a pedestrian, albeit important, problem. And so buried in here are a bunch of interesting theory questions that came up along the way. But I'm also going to tell you about bridges. Okay, so I should say this is joint work with Jae Young Park, who is a graduate student at Michigan, and Mike Waken, who is at the Colorado School of Mines. Okay, so yes, I'm sorry, Ronit. These are pictures of collapsed buildings to emphasize that it's important to assess the structural integrity of things like the I-35 bridge in Minneapolis. Jay tells me that this was a department store in Korea that collapsed. He remembers this, and so it's critical that we monitor these things. And so my colleagues in the College of Engineering and Civil Engineering have developed a platform, a wireless sensor platform that they stick on bridges and buildings and ships all over the world. And these really cheap sensors can acquire vibrational data. So they sit on a structure and they just measure how much the building shakes. And then they transmit their data to a central node. So these little wireless devices, they're like about this big. They take 6 AA batteries, and so changing the batteries in these things is a major pain in the neck. In order to go and instrument a bridge, they have to close a highway. They have to get MDOT, Michigan Department of Transportation, out to, with their cherry pickers and so on. So they would really like ways of acquiring data or ways of transmitting data, basically ways of dealing with their data that conserve battery life. Better yet, they want to be able to use solar panels instead of AA batteries. And Michigan doesn't get a lot of sunshine. So especially in the winter, they discovered that the north side of the bridge is particularly cloudy. I don't know why this was news to them. I knew this. So they whether on purpose or accidentally, have tremendously undersampled, randomly missing data. So they would like to know what can they say after collecting data over a winter. And they would like to be able to accurately assess the health of the bridges and the buildings. Just in case you think that the bridges that they put these things on are going to fall down anytime soon. Really what they're doing is they're just keeping an eye on the bridge. They're not trying to decide, is it going to fall down in the next 6 months? Does it need repairs? Another thing that they are trying to do is to populate, say, finite element models of these structures so that they can, analyze various scenarios. So it's not so much to determine whether or not an earthquake in Michigan would take out bridges. Okay, so I guess I sort of like to make the point here that their data are not necessarily huge, but their devices with which they use to acquire and transmit and process the data are tremendously resource constrained. And sort of the dual of big data is incredibly small computational power. And literally batteries, 6 AA batteries, you can't power a lot. So, sort of the dual of big data is small resources. So this is a beautiful example of small resources. Okay, so what is the math problem? Enough about engineering. What is sort of the math setup? So they have N sensors that they place on a bridge, say, and each sensor is going to observe some displacement data. So how much does the thing move up and down? And let's say that we concatenate this data, all of these sensors. So over time, each sensor is like a great big column vector. And what is a reasonable model for the shaking, the vibration of a bridge? Well, a reasonable model, or the very simplest thing that you would start with, is to model each one of these little sensors as a little spring, and all of these little springs are connected to one another, just say in a straight line. And so you have a really simple system of springs, and this is modeled by a really simple system of second-order ODEs. I never thought I would say that in a talk. Okay, so here we go. We've got a mass matrix, a second-order, differential, second-order derivative in time, a stiffness matrix, and absolutely no forcing. They assured us that the segment of data that we were to analyze, there were no trucks, cars, whatever, passing over the bridge, and so there's no forcing applied to the bridge. This is purely homogeneous setup. Okay, so I have to teach PDEs, so I can solve this. This system of equations, and they have a beautiful solution as a sum, a linear combination of sinusoids with different frequencies and different phase offsets, multiplied by what the civil engineers called mode shapes. You can think of these just as the generalized eigenvectors of the Laplacian applied, in space, purely spatial. So these guys are, purely functions of space only. These guys are functions of time, and the civil engineers call these things modal frequencies, and they call these things mode shapes. They're eigenvectors of the Laplacian, so they are real. They form an orthonormal basis, and they give you physical information about the structure of the bridge. And so Jay computed some examples, and these are the fundamental vibrational modes of the bridge. It looks like the bridge really oscillates a lot. He doesn't have any of the magnitude on here, but these are the fundamental frequencies at which this particular bridge vibrates, and these are their fundamental shapes. So these mode shapes give the engineers structural information about this bridge. And so what they want to do is they want to, from their N sensors placed on their bridge, acquire in a very power-efficient fashion, or transmit in a power-efficient fashion, their vibration data, and from that, say at some central location, not on a really cheap wireless device, they want to extract these modal frequencies and these mode shapes. So they call this modal analysis. Anyway, that was what our goal was to do. So we said, all right, that sounds great. Let's take this fundamental solution and let's just consider these sine waves with different frequencies and different phases. Let's just look at them as complex exponentials with frequency omega sub n. And so here we've got a superposition of sine waves in time that are multiplying these mode shapes in space. And we are going to sample this solution at m different points in time. Okay, so we've got n sensors, n different physical locations on the bridge, and m different positions in time, right? So we have a matrix, right? Okay, good. Now we're all in the realm of big data, big-ish data and matrices. Okay, so here is the, enough with these PDEs, Anna. So here's our matrix of data. You know, I've told you what each entry looks like, and you know, here's the general solution. So we'd like to know from this data, can we extract the mode shapes of the bridge? Can we do so in a relatively efficient fashion? Sort of the flip side of that question is if the sensors cut out and fail to record data over various, you know, at certain points in time, how accurately can we figure out these modal frequencies as a function of how close together they are or their general extent? And then also, how accurately can we figure out these mode shapes? Okay, so I have to tell you that we spent 6 months trying to figure out what in the world the civil engineers did that they called modal analysis, because it seemed rather straightforward just to take an SVD of this data matrix. And the reason is that if you unwind this superposition, you've got unitary mode shapes over here. You've got a diagonal matrix that is an amplitude these are on the diagonal are the amplitudes of your solution, and over here you've got sampled sinusoids, right? So you've got n different sinusoids at n different frequencies, and they're sampled at m different points of time. And so, you know, this looks like an SVD. Okay, so the first question we asked was, how can we make, or should I say, what sort of sampling patterns will give us a nearly orthogonal matrix over here, so that we really and truly can just do an SVD and tell the engineers, look, your mode shapes are the right singular vectors of your data matrix. Does that make sense? So far, all we're doing is, you know, the mathematician's approach to modal analysis, and you know, what can we tell them about you know, different trade-offs in sampling patterns. Okay, so this is like step 0. Okay, right. So the key idea is, you know, we want the right singular vectors of this data matrix, and how accurately the right singular vectors of the data matrix, how accurate they are. This accuracy depends on when we sample, in time. I'm not going to say anything about where to put the sensors in space. Let's just assume they tell us where to put them. Okay, how many samples we collect, how many samples in time, and also how long we sample for. So it's not only how many samples in time, but also how long we sample, how long we observe for. So the number of samples, the total sample duration, and then 2 quantities which seem quite natural for harmonic analysts is the minimum separation between modal frequencies. So these modal frequencies do not lie on some beautiful discrete grid. You know, we're talking about a bridge, and so these are you know, frequencies that you know, let's say could be any sort of real number. We'd like to be able to say, you know, if you sample for such and such a length of time, and you collect so many samples in time, you can resolve modal frequencies that are close by to within this minimum separation. Okay, so that's really how they wanted to use this sort of information. And the accuracy of these singular vectors also depends on the maximum separation between modal frequencies. What is the lowest frequency versus what is the highest frequency? Okay, so I'm not going to give you almost any proofs. I will just give you sort of sketches of proofs and sort of highlight the main ideas. So the very first thing that we said was, okay, how are you sampling right now? And I said, right now we are sampling uniformly, deterministically, with the following sampling rate. And we said, okay, let us tell you how well you can resolve your modal frequencies and how accurate you can get your mode shapes, just right off the bat, with this incredibly simple brain-dead scheme. So we've got uniformly spaced samples in time. Their sampling interval is something like 1 over the maximum spacing of the frequencies, the maximum spacing of these things. And we sample for either log n over epsilon times this ratio, or at least n samples. Then we can get the mode shapes. So the error between the mode shapes returned by the SVD and the honest-to-God, ground-truth analytic mode shapes. In other words, the right singular vectors from the sort of truncated discrete data versus the honest-to-God singular vectors from a supposed analytic solution. The L2 distance between any two of these pairs is bounded by roughly a constant times epsilon, and then times some sort of gap here that looks like a spectral gap. Right? So these are the magnitudes of the here. It's these amplitudes here that we attach to these individual analytic solutions. Okay, so if these guys are really close together, in other words, if you think of these as the singular values, if these guys are really close together, then you're going to have some trouble. But if they're fairly well separated, then you're good. Okay, so this is how accurately these guys can do with their current sampling scheme. Okay, even this was news to them. Okay, if you can do something, uniformly deterministically, why not do it randomly? After all, their solar detectors are only sampling, let's say, randomly, because they drop out every now and then. So let's say that you sample uniformly at random. Now, I'm not making any sort of discretized time. This is purely a mathematical result. We're going to sample uniformly at random over some interval 0 to t, and we sample our duration, let's say, is log n divided by the minimum frequency spacing. And we collect roughly n log n over epsilon squared samples randomly within this time period. Then with exponentially small failure probability, the mode shapes that are returned by the SVD are also pretty close to the true, to the analytic solution mode shapes. Okay, and again, we pay some sort of price for in the spectral gap of the analytic solution. Okay, what did I want to? I'm missing a slide. Where is my slide? Okay, all right. I'm not sure if the summary is here yet, but we'll see what happens. Okay, so neither one of those two settings that I described is very practical in terms of in terms of truly saving power. So what really costs on these little wireless sensors is transmitting information. It's basically turning on a radio and transmitting data is very expensive. Actually collecting the data and storing it in memory is not so expensive. So one thing that they asked us to do is, okay, we'd like to transmit less data. So one model that we came up with that seemed fairly reasonable and seemed like something that was sort of consistent with what they could implement was the following model. So it is possible for them to sample uniformly, deterministically on a fairly fine grid, but it costs them too much to transmit that data. You have a question. Do the mode shapes change? What do I know about civil engineering? So yes, they do change. I don't think on the time scale over which they collect this sort of data. So I believe that they probably are going to do this maybe every couple of years. Recalculate mode shapes. Maybe they're going to do this 2 times a year, maybe winter and summer. Bridges contract in the winter and expand in the summer. Maybe they want to do this. Buried in your question is how much memory do they have? Can they store all this data for 6 months and then come and download it? And I suspect not. I think not. Really and truly, these things drop data fairly frequently, and so it's not accurate to say they're collecting data continuously, because they're not. How often do they dump the memory to some central location? I don't know. I don't know if it's once a day, whatever. I do know that the power is a tremendous issue. The radio is very expensive. So we came up with some solution. Right, it's not that hard for them to have a clock that runs that has fairly high frequency, and it's not that hard for them to collect a sample. It's not that hard for them to be able to collect a sample on this uniform deterministic grid. It is too hard for them to collect data randomly in time, right? Randomizing a clock on these little sensors is actually kind of a nuisance. So what they can do is every clock cycle multiply by a random plus minus 1, and they can add these things up. Random, pseudo-random, whatever. That is actually fairly easy to do. Messing with the clock is hard to do. So as long as you are, okay doing some sort of, say, random linear combination on a regular grid, then you're okay. So we said, all right, that's a good model. So I'm not saying, sample, uniformly at random in time. I'm saying, take a dot product with a random plus minus 1 vector of the samples that, it's okay to collect, okay? And accumulate those and sum them up and transmit them, right? So it's easier to transmit one number here that is a random linear combination of the samples. It's easier to do that than to transmit all the samples. I'm not saying that it's hard to take each sample, okay? Does that distinction make sense? Okay, good. Okay, so mathematically, what are we saying? We're saying you have uniform deterministic sampling with which you have hit with say, a Johnson-Lindon-Strauss matrix, okay? And you have then transmitted that sketched data, okay? So let us suppose that these samples, these M time samples, are uniformly spaced. This is your sampling interval, and you have taken this many of these uniformly spaced samples. if you, and you've, mathematically, you've built this matrix X. If you then hit that on the left with a Johnson-Lindenstrauss transform, and how many rows do you have in that? Let's say you have the rank of X divided by epsilon squared. I don't know why there's a prime there. So that many rows, notice the number of, then you have a much shorter matrix Y. It still has as many columns as X did originally, but it has fewer rows. So each sensor has less data to transmit, but you have not reduced the number of sensors. Okay, I'm also, assuming that each sensor has the same phi inside it, that all of the clocks in each of the sensors, they're all synchronized, et cetera. Okay, so if you then look at the SVD of Y, remember we're interested in the right singular vectors of X. If you look at the right singular vectors of Y and ask how close are they to the original right singular vectors of X, well, with high probability, they're pretty close. How close are they? You're going to pay 2 error term penalties. The first one is the first error term penalty we've already seen, just in terms of how far off are the singular vectors of X from the analytic mode shapes. Okay, so that's this error term. We've seen that before. And then you're also going to pay a penalty for doing the sketching. And that penalty is this error term. And you'll see, I'm also, yet again, paying an error term for the spectral gap in the singular values of X, not in the singular values of the original analytic signal. Okay, so I think it was Michael on the first day who said, there are lots of real, scientific, engineering, whatever applications where you care about, not just the rank 1, rank 2 approximation to your data, but you care about, the rank K, for K large approximation. And so this is an application where the rank K approximation to X is not actually what you want. These guys really want these mode vectors. They want these mode shapes. They want to know how far is the true mode shape from what you've returned. So they're not interested in using their data matrix X to solve a linear algebra problem. They really want to know physical properties about the bridge, and their physical properties are these K different mode shapes. Yes, Petrus? Yeah. So rotations wouldn't. Okay, so. Yeah. Yeah. Okay, so buried in here is we're this between -1 and 1 business accounts for flipping the sign, whether you have this plus V or minus V. So that's basically one way to get around this. Another thing is to use the spectral gap. If the singular values are exactly the same, the singular vectors are, they're lying in a subspace, up to some rotation, that gap is 0. We can't promise anything, but that's okay. In these applications, there are gaps, and when there aren't gaps, we can't promise anything, which it's exactly what you would expect from linear algebra. We're not interested in a subspace. We are actually interested in the vectors, to the extent that they're different. Okay. Yes, here we go. Okay, so every time I drive to the airport, I see this bridge because it is on the way to the airport. So this was the bridge where they actually put in a bunch of sensors, and it's an IPSI. So we asked them for data. We want to know, how good is this? So they had 18 sensors on the bridge. They had, they assured us that yes, the time snapshot that we're giving you, this stuff has these free vibration. We're pretty sure there were no trucks or cars driving over the bridge at this point in time. And Jay used his favorite Johnson-Lindner-Strauss transform, not necessarily mine, but his, to sort of simulate, if we had collected data in this fashion, what would we have gotten? And so here are his 3 dominant modes. These are the fundamental modes that the bridge moves in. And he tried a couple of different methods. The really embarrassing part of this work is that we kept asking the engineers, well, what are the mode shapes? No, really, what are they? And they said, there is no gold standard. There's just a catalog of algorithms. Pick some. And we said, OK, that's awful. And I said, how should we evaluate? Well, the dot product or the difference should be more than 0.9. So what does it mean? We got to be like 90%, 90% accurate? Yeah, 90% is good. So, this is awful. Okay, so anyway, we went down from 3,000 uniform samples in time to 50 measurements at each node. And we had a bunch of different methods for computing. This must be the error, not, yeah. This must be the error, not the actual dot product. So we actually did fairly well. I wanted so FDD is the one of the gold standards in their book. I also wanted to do sort of the stupid sanity check that reconstructing each column using some generic compressed sensing algorithm, reconstructing each column and then using the so-called gold standard algorithm was not nearly as accurate as just looking at the singular vectors. So signal reconstruction is not always the best thing to do. Okay, so we also so I'm also interested in Fourier sampling algorithms. So we also asked Jay, let's go estimate these modal frequencies because this is kind of interesting. So let's look at the left singular vectors of x, or the left singular vectors of y, and let's just take the FFT of these things, and how accurately are we getting these frequencies? And we do okay, I think was Jay's sort of answer. It requires some eyeballing to look at the peaks in these in the spectra and say, yes, that's the big peak, that's the big one, that's the big one, et cetera. So this is a real ad hoc algorithm. It's not great, but it's kind of interesting that it works fairly well. Okay, so what's yes? I'm sorry, how can you what? Not have a problem with spectral gap. You think bridges are perfectly, exactly, beautifully symmetric. You should drive to Michigan. I assure you, there's nothing symmetric. Okay, so it's great to tell stories about bridges and things falling down, but there's some theory hiding in here. So I guess the big theory that's hiding in here is what do I want to do? Yes, is sketching a tall, thin data matrix on the left, so that you're sketching down each column and collecting a shorter matrix but not a thinner matrix. And when the right singular vectors of your sketched matrix are close to the right singular vectors of the original matrix. What's kind of cute about using a Johnson-Lindenstrauss matrix is that this can be done column by column in each sensor. And it's easy to update these kinds of sketches if you see changes. So it's kind of cute. Yeah, so here's the result. Well, I mean, we sort of summarized it in talking about the mode shapes of the bridge. Okay, so all right, so more formally, what is the result that we get? Well, it's not a surprise to anybody that we get a relative error approximation to the singular values. That's sort of been, this is, you know, just one example of where this has been shown. And then we also get the right singular vectors, again, you know, up to this spectral gap. So as long as these singular values are not equal, and also that they're fairly far apart, then we get an L2 distance between each singular vector and the true singular vector that's bounded by, you know, something that's roughly epsilon times some function of the spectral gap, 1 over the spectral gap. Okay, so how does this work? Well, this works. This is just sort of a standard using matrix concentration results, as well as looking very, very carefully for the exact right matrix perturbation result. Somebody somewhere proved this, and you know, you just have to look hard enough. You know, we have our sketch of the form y, which is phi times x. So this is the SVD of x. Notice that if you form y transpose y, that's like x transpose phi x. Sitting in here in the middle is phi transpose phi. Remember, phi transpose phi is a Johnson-Lindenstrauss matrix. So it's almost the identity. It's the identity plus some perturbations. It's a good thing we have at our disposal matrix perturbation results. Okay, so here, if we write out what y transpose y is in terms of a perturbed version of the identity from phi transpose phi, here is the original. This is, you know, truly what we desire to find the eigenvectors of. And then here's this perturbation. And we're interested in how far off the eigenvalues of this matrix are from this matrix given this very special form of a perturbation. Yes, so if you go look in this relative error matrix perturbation result by Mathias and Veselik, 1998, then this is exactly the sort of analysis that we want. Okay. So there's, I guess in the last couple of years, there has been quite a bit of interest in sort of compressed PCA or compressed SVD. So these are just two examples of this work. I know Konstantin is going to give a talk on Thursday on this sort of problem. So these guys, both Fowler and Cui and Hughes, were interested in the left singular vectors rather than the right. So their aspect ratio is slightly different, and they're actually interested in sketching in a different dimension. They actually use different random projections for different columns. It's sort of a peculiar setup. And then, you know, of course, we've heard a ton in the last day and a half on subspace approximation, low rank approximation, et cetera. And you know, all of this work focuses on finding approximate subspaces rather than individual vectors, primarily because subspaces are really useful for forming projectors, forming orthogonal projectors, for solving least squares, for solving regression type problems, for solving linear systems. Some of these require multiple passes over the data, or sampling according to certain kinds of probabilities, et cetera. Yeah, so we heard lots and lots of talks about this. So these are all intimately related, but this is an application where the subspace will not suffice. So they really need these vectors. Okay, so let me conclude by saying, we started out working on this problem. I started out explaining this to you as a acute application, but embedded in it are a bunch of kind of interesting theory problems. So there's questions about Fourier sampling. So how long and what sort of sampling rate do you need in order to basically resolve close by frequencies in a Fourier sampling type problem? Compressive SVD for the actual vectors themselves. And what's kind of fun is that I can really worry about how big is epsilon squared, or 1 over epsilon squared, because this is an actual hardware platform that a graduate student can program, not me, but they can actually implement this, and they can test it out. And it's really kind of interesting to write papers with the engineers, because they don't care so much about constants and epsilon squared. They would like to know how much longer their batteries will last. So it's very interesting to talk trade-offs with them. Okay, so future work for the modal analysis stuff. Our little analytic solution is kind of a joke. This masses and springs connected with absolutely no damping, no forcing terms whatsoever. So a more realistic model would be a good thing. Our ad hoc algorithm for estimating the modal frequencies is intriguing, and we have no theory analysis for that whatsoever. And finally, there's a good reason why the civil engineers have more complicated algorithms than just take an SVD, because there's all kinds of noise and stuff that's in their data that we haven't taken account of in sophisticated estimation strategies. And then finally, I promised in my abstract something kind of intriguing, and a couple people have asked me about it. So a few people observed, and I even said a little bit, that these mode shapes they're nothing other than the generalized eigenvectors of a Laplacian. And in this really simple mass system, they are nothing other than the eigenvectors of a Laplacian for a really simple graph. In other words, the graph that's simply a line with like n vertices on a line. So you could ask, right? So basically, this vibration business is nothing other than solving the wave equation on a graph. And you could ask, there's all this beautiful spectral graph theory that's useful for solving the Poisson equation on a graph. You could also ask about more sophisticated graph analogs of more sophisticated types of PDEs, and where your operators are not just a Laplacian. And so I have been working with people on the forward problem for PDEs on graphs, but also the inverse problem, where you try and infer structural graph properties by probing the edges of the graph. And so I like to think of this bridge problem as like inferring the structural properties of a really simple graph and the graph analogs of PDEs as some sort of a nicer mathematical generalization thereof. Okay, so thank you. So we haven't analyzed that at all. That's part of the more sophisticated estimation strategies. So I should say the civil engineers, when they actually do this analysis, they'll like break up their data into chunks and sort of average the answers they get, roughly speaking, average the answers they get over chunks of time to try and average out noise. So that is one sort of gross approach that they use currently. Yes, Fernando. So I don't believe that that's true. I believe that these sensors are sophisticated enough that the clocks are synchronized. They've got like GPS. Yeah, they're resource constrained, but not that bad. So the clock synchrony is actually not. It's not. I mean, it's a good math question, but I'm not sure it's a practical issue for them. David. Yeah, I don't know. I mean, it seems like. So right now the model is everybody is synchronized, and the experiments that we did, everybody was synchronized, and everybody got hit with the same JL matrix. Ido. Sure. So there could be. No. Because there could be some initial condition that has set them vibrating. So imagine you've got a string, and your initial condition is to raise the string up like this, and you let it go. There's no forcing right now, but maybe a color just. Yes. So it's a difference between initial condition and no, it's not a stupid question. It is traffic, but just not at the secondary. That's right. Yeah.
Do you have an example of a combinatorial property that you can study on a PDs?
No. This is purely nice math. I should say not yet. No.